Welcome everyone to this talk where we'll be showing you how we generated test cases from a context-free grammar using graph traversals. Before we get into the details on exactly how our algorithm works, let's first talk about what the problem is that we are trying to solve. So essentially, we are generating test suites for a unit under test from a context-free grammar, and there are two kinds of test suites. So positive test suites are those that contain words that should be accepted by the unit under test, and negative test suites contain words that should be rejected by the unit under test. From this behavior, we can see that the unit under test acts as a decider. So typically these are parsers, but really it can be any system that acts as a decider. The goal is that we want to ensure that the unit under test will accept all valid words and reject all invalid words in the language without actually having to test the entire language. So this means that our test suites are essentially a subset of the language and a very specific subset of the language such that we can guarantee this behavior. Existing methods for producing test suites from context-free grammars focus mostly on the grammar's production rules. So we wanted to take a slightly different approach, which is looking at the LR-Automaton that corresponds to the grammar. Specifically, we wanted to cover all states and all transitions in the automaton, since the automaton at an abstract level models the parser's behavior. And if we can cover all states and transitions, we can be sure that we are covering most behaviors that the parser might exhibit. In order to use graph traversals on the automaton, we had to devise a construct that we call an LR graph. Functionally, this is identical to an LR automaton. However, instead of shift transitions, you have push edges, and instead of reductions, you have a combination of a pop edge, which removes a certain number of items from the stack, and also a corresponding push edge that pushes a non-terminal symbol onto the stack. So in the graph on the right, you can see that the push edges are denoted by a solid line, and the pop edges are denoted by a dotted line. So if we look at an example of how this test case on the right might be represented in the LR graph, we can see that initially we first have to perform a pop corresponding to an epsilon reduction, and then also the relevant push of the non-terminal symbol. Then we go to the push on the open bracket, and we then again have to perform a pop and a push to perform the epsilon reduction. And then we'll head to that push edge, perform the relevant reduction, and then go to the accept state. It was very important to us to be able to ensure that our algorithm would always terminate regardless of the LR graph that it was traversing. We therefore decided to use breadth-first search, since it performs a layer-by-layer exploration of the graph, so cycles wouldn't pose a problem. This is very important since we couldn't use standard cycle detection, since certain edges needed to be covered more than once in order to end up with a valid path, as can be seen with the edge between 0 and 1 that is covered more than once in the valid path for the opening and closing bracket example. Our algorithm has two phases. Phase 1 generates a set of prefixes that cover all the edges, and then phase 2 is responsible for taking these prefixes generated in phase 1 and then transforming them into valid paths, and then that corresponds to valid words. Both these phases rely heavily on breadth-first search to explore the LR graph, although they work in slightly different ways since they have different goals. So if we look in more detail at the flooding phase, we can see that it is essentially breadth-first search. If we look at the left here, where you have a queue, except we don't run until the queue is empty, but instead we run until we have seen all the edges in the graph. But then the rest essentially works exactly the same as breadth-first search would, except that you've got certain conditions on when an edge might be taken, since you cannot always perform any reduction, and it relies on the prefix that has reached the state from which the reduction has to be performed. The easiest way to understand how all of this works is by looking at the example from before. So initially, you can see that the only action can be performed is the epsilon reduction, after which we can either go to the accept state or we can take an open bracket. then it performs another reduction, and from this point on it can either take another open bracket or close that and then perform some more reductions. As we can see, both of these paths from the split are being completed in parallel. Then from this point onwards we see that the top path can either go to the accept state or it can keep on pumping out longer test cases. And then in the bottom path, the next possible move that it can perform is this reduction. And then at this point the flooding phase is done since all the edges are covered, even though, as we've just seen, there are still prefixes on the stack which aren't valid paths yet. The path completion phase works very similarly to the flooding phase from before. It also uses breadth first search, except that it will keep on running until we have found a possible path that ends at the accept state. The easiest way to understand all of this is by once again looking at an example. So we'll continue the example from before, where we ended up with the pop edge from state 4 to 2. So the next action that needs to be taken is the push edge from 2 to 3, after which we have a choice of either continuing with an open bracket or a closing bracket. Now we can see that the closing bracket is going to lead to the shortest path to completion. However, in practice the algorithm won't know this extra information, so it will actually keep on exploring both these paths in parallel until it finds a path that ends at the accept state. And the first path to reach the accept state we know will be also the shortest path to completion, since breadth first search explores the graph in layers. So then we can see it will just go around here and then to the accept state. Our algorithm up until now has been looking at how we generate positive test cases. Now we use the same idea when we generate negative test cases. However, we perform mutations on these positive test case paths, and specifically we want to perform mutations that guarantee an invalid word without having to perform some check afterwards. So in order to do this, we define two concepts, namely the follow set, which is just the set of all tokens that can follow any state in a valid derivation, and the almost accepting state, which is just any state from which we may reach the accept state without traversing any further terminal push edges. So we have four possible mutations, the first of which is insertion. This basically entails just inserting a token after a state on the condition that that token is not in the follow set of the state. So we can see an example here where after state 1 we can insert a closing bracket, since the follow set of state 1 only contains an opening bracket. Then for deletion, we delete terminal push edges if the source state is not almost accepting, and also it does not overlap in its follow set with the destination state. So in this graph there are actually no edges that can be deleted, since all edges here are either almost accepting, as is the case with, for example, state 4, where from state 4 we can go to state 0, to state 1, and then to the accept state. So that doesn't include any terminal push edges. And then we can also see that, for example, in the follow set of state 1 we have an opening bracket, and in state 2 we also have an opening bracket, since the open bracket from state 3 to 2 may be reached without any other terminal push edges in between. Next we also have substitution. That works very similar to insertion, except instead of just inserting a token after state, it will swap the token on terminal push edges. So we do this when we once again can see that the token is not in the follow set of the source state of that edge. So for example, we can swap the opening bracket on this edge with a closing bracket, since the follow set of state 1 only contains an opening bracket. Then we get cutting, where we essentially terminate a word before it is a valid path. And we can do this when ever a state is reached that is not almost accepting. We can do this after state 3, since the only way to leave state 3 is by either pushing an open bracket or pushing a closed bracket. As we can see with the examples from the base algorithm, there are sometimes paths which are not required in order to cover all the edges that are taken due to the non-deterministic approach that we're taking with breadth first search. Now, on certain inputs, this can lead to an exponential growth in the queue size, which results in a very slow running time. So we wanted to improve this while still keeping the same termination guarantee and also still keeping the same guarantee of covering all edges and states. So we did this by turning the queue into a priority queue. So in the flooding phase, this meant that new edges that are covered have a higher priority than going over an edge that we've already seen before. In the path completion phase, this was a bit more complicated. We essentially checked which edges were part of a loop, and then we prioritized the edges that were part of the loop that decreases the stack height the most. So we compared the results that we got from our base algorithm, which is shown in the LR column, and also with this improved priority algorithm, which is shown in the LR star column, with the current grammar-based testing methods which focus more on production rules. We can see that, for example, in this grammar that we used here for expressions, our coverage that we achieve is comparable to the step 3 and the BFS3 algorithms, and also that in terms of number of test cases, that the original algorithm sits somewhere between the number of test cases generated by step 3 and BFS3, whereas the improved algorithm tends to be closer to the number of test cases generated by step 3. We've actually since improved the optimized method so that the LR star method now actually produces even smaller test suites than any of the other methods that produce full coverage. So in conclusion, we have shown how we now have a new analytical algorithm that we can use to produce a test suite that gives us guaranteed coverage of all states and transitions in an automaton, and therefore also of most behaviors that the unit under test might exhibit. However, we also still have a few performance issues left to address, even though the prioritization method already improved performance a lot. One of the areas of future work that we have identified is dealing with so-called stubborn edges. And these are edges which just refuse to be covered efficiently even by the prioritization method. This represents the last hurdle that stands in our way of using our algorithm on production level grammars. Then we also want to investigate negative test case generation through stack mutations, since the current mutation methods focus more on edge mutations. Specifically, we identified two types of stack mutations that we're interested in, namely stack jumping, which is just changing the target state on a pop edge in a reduction, and then also stack scrambling, which shuffles the stack's contents. Thank you.